I thought it would be better to actually just devote 2 lectures to NMR spectroscopy, because this is something that I think is important. It's a routine technique which is used, if you're a chemist, every day, and particularly devote some time to heteronuclear NMR, which is something that I'm sure you haven't done, except maybe for phosphorus and fluorine, and look at some other nuclei, for example, silicon, tin, and so on. So, yeah, I think the important thing to start off with is some comments about how one about hardware and how one should sort of prepare the sample. Basically, there isn't a golden rule as to how much sample you need for a good quality NMR spectrum. It really depends on a number of factors. Particularly the molar mass of the compound. If you have a protein, you're going to need more of it than if you, for example, record an NMR spectrum of methanol, right? Because they've got different molar weights. It also depends what nucleus you're recording the spectrum of. If you record a proton NMR spectrum, you need much less of the sample because it has a much higher natural abundance. If you record an NMR spectrum, a 13C NMR spectrum, you need much more because it's got a lower relative abundance. Same with silicon. So that's an important point. It also depends on what sort of system you're using. How sensitive is the probe? So there's some technical issues that one has to look at, and also what sort of experiment you're doing. So in NMR spectroscopy, we talk about doing NMR experiments. You know, like are you doing a 2-dimensional spectrum? Are you doing a 1-dimensional spectrum? Are you doing a depth spectrum? You know, it really depends on a number of factors. But here are some sort of hard and fast ideas of how much you would require. So for a 1H NMR, you would require about 1 to 5 milligrams for an average weight molecular compound. What means average weight? Well, maybe 3 to 400. Of course, if the molar weight increases, you need to add more. And as you can see for a 13C, because it has a lower natural abundance, you need much more, approximately 10 times more. Now this is the requirements for 400 megahertz NMR spectrometer. So different spectrometers have different operating frequencies, and traditionally, well, in the olden days, you know, like let's say in the 1960s, they were 40, 30 megahertz. Today, routinely one uses 400, 500, 600 megahertz spectrometers, which have a much better resolution. Now I include here a note on solid state NMR. We mentioned this in one of the lectures briefly, the lecture on cyclopentadienes. It is possible to also do solid state NMR. So what we're talking about here, and what we're going to be talking about today, is solution NMR spectroscopy, but solid state NMR, so-called magic angle spinning NMR, also exists, where it's possible to take a solid and basically you put it in a ceramic rotor, compress it, and well, of course the hardware is completely different, but it's also possible to record NMR spectra of solids to see what the thing looks like in the solid state. And sometimes this is very important, right, because what you see in solution is different to what you see in the solid state. And it's a very useful technique. You can do solid state NMR spectroscopy, for example, with a range of different nuclei, silicon, phosphorus, 1H, etc. So here's some more technical comments. Of course, we need to use deuterated solvents. This is important because we need deuterium to get a lock signal when we're recording the spectrum. And of course these solvents are expensive, right? So for example, deuterated THF is extremely expensive. And so what some people do to save costs is they basically, instead of dissolving the whole sample in the deuterated solvent, they basically just add a capillary. So you can basically fill a capillary with a deuterated or deuterium-enriched solvent and put that in the NMR tube with a normal solvent, and that enables one to get a lock signal so that you can actually record the spectrum. NMR tubes need to be cleaned and unscratched. generally, well, here in Maastricht, we don't really reuse NMR tubes. They get used once and discarded. But where I was working before, we had to reuse them, and then of course they get old and they get scratched, and you record spectra, and you get sometimes spinning sidebands and all sorts of unpleasant things, which basically ruins the quality of the spectrum. So one has to look at these technical issues very carefully. When you're working with air-sensitive compounds, of course, you have to be careful that it's perfectly sealed. So you've got to look that the cap is not, pierced or permeable. And generally, when one's working with air-sensitive compounds, one uses an NMR tube that's different to the one that you've been using in the practical. It's called a Young type NMR tube, which is basically a glass tube with a so-called rotor flow stopper on top, which seals it completely. And that keeps the sample safe, and you can do long-term measurements. But even for extremely sensitive compounds, you can record an NMR tube in a normal NMR tube like yours. Let's say if you prepare the sample in the glove box and you seal it off with a bit of parafilm, generally that's good enough for a proton and a phosphorus spectrum. But if it's a very sensitive compound and you try to record, let's say overnight, a C13 spectrum, it's probably going to decompose. So one must think about these things and take the sensitivity of the compound into consideration. Very important is that there should be no precipitate in the NMR tube. This just completely ruins the spectra. And this is what you see, what you tend to see if you have a precipitate in the spectrum. You see, you lose the resolution. So what we see at the top here is like an ideal sample preparation, just the right height. Generally about 2 fingers, right, is the right height of the solvent, maybe a little bit more than 2 fingers in the tube. It shouldn't be over-concentrated. If it's too concentrated, you also end up with spectra that look like this, so with very broad signals. And yeah, you can see clearly the difference between the top and the middle and the bottom spectra, right, in terms of resolution. So here you can clearly see very sharp signals. Here they're broad, we have a loss of resolution there. And if we don't add enough solvent, we end up with something that looks like there's a complete loss of resolution. I mean, you can't even see the coupling pattern. You can see here we have doublets here. So you wouldn't be able to, for example, determine the coupling constant. So it's very important to record the spectra from well-prepared samples. Now, let's talk a little bit about how NMR spectroscopy works, very briefly. Today's lecture, I don't want to be about theory. That's something for a spectroscopy course. I'm going to mention it in parts. I want today's lecture to be sort of to equip you with the tools to be able to do hands-on analysis of compounds in organic chemistry. In other words, I'm not going to get lost in theory. We're going to look at lots of examples, right? Okay. So this is the basic idea, right? And some of you have probably seen this, but you can think of spin-active, NMR-active nuclei as being little magnets, right? And if you take a sample and you basically sum all those magnets together, you can imagine that they process about, in this case, the z-axis, depending on their environment. If we then apply a pulse, a radio frequency pulse, and modern NMR spectroscopy uses pulse techniques, so that we apply pulses, you get these into basically an excited state, if you will, and after that pulse has been applied, we generally have a period of time where we allow these excited nuclei to relax back to their equilibrium position. And this takes on various forms. We have different types of relaxation mechanisms. For example, T1 relaxation and so-called T2 relaxation. That's not so important. But they relax back to their equilibrium position, and we generally then detect that process of relaxation, and we end up with something that looks like this. This is called a free induction decay signal, where we plot the intensity, if you like, of these. So we're representing these magnets or these spin active nuclei as vectors. These are relaxing, and you can imagine if they move out of the z plane back into the xy plane, the intensity in terms of the z components is going to decrease, and we're going to get a free induction decay signal. So it decays as it. So what this is really a reflection of this relaxation process, right, back down to equilibrium position. And this is, of course, an intensity time spectrum or graph, because we're recording it over a period of time. And mathematically, we can perform a Fourier transform to convert that to the time domain here to a frequency domain. And I guess many of you have seen this. So we have this decay, we perform a Fourier transform, and we obtain an NMR spectrum, where the x-axis is now in terms of frequency, not time, and the y-axis is in terms of essentially intensity. Now, traditionally, instead of working with frequencies on the x-axis, we work with parts per million. That's just a matter of convenience, because having to slide frequencies would, of course, not be very, very convenient. This is what it looks like so this is sort of the mathematical description. This is what you would ideally see in real life. So here we have a classic free induction decay signal for a sample. We perform a Fourier transform, we get the spectrum. So that's the mathematics behind it, very simple. This, for example, will be a carbon-13 spectrum, right? So, but the principles are always the same. Now what we have here is, what I want to mention now is this notion of decoupling, which is very important. Now, in your practical, you might have seen on the spectrum something that looks like this. Now, that curly bracket with a 1H, what does that mean? It means you're recording a 13C spectrum and it's decoupled from the 1H. In other words, you're going to record a spectrum, find all the 13C signals, but you're going to switch off any coupling to 1H's. That's what that curly bracket means. Same thing with phosphorus. You can have a phosphorus 31 decoupled spectrum or a phosphorus 31 coupled spectrum, meaning that you're going to see coupling to protons in particular. Right now, so this is this notion of decoupling, which is very important because, as you can see here we have an organic compound, and what we see here, if we don't decouple, we end up with a very complex, so this is the 13C spectrum, we end up with an extremely complex spectrum, and it's complex, we have many lines in it because we see all the coupling to the protons, right? So you can see, for example, all of these carbon atoms here, well, not all of them, but most of them, have protons attached to them. And if you don't switch off the coupling to the 1H, you see those couplings. So you end up with all these multiplets. And so it's very difficult to make heads or tails of what's going on. If we switch that off, so here you can see what we're actually doing. We basically just, we do a broad band decoupling. So that basically kills all coupling to protons. And you can see at the bottom here, you end up with a very nice spectrum where you just see signals for the carbon atoms. Do you see that difference? So let's take a look here, for example. This OCH2, this corresponds to this carbon atom here. Remember, this is a 13C spectrum. You can see in the coupled spectrum, it appears as a what?
Triplet.
Triplet. Yes. Why a triplet? Because it's coupling to two protons, which are equivalent. And if it couples to two protons, which are equivalent, 2 plus 1 is 3. And we switch the coupling off and we get a singlet. Let's have a look at, how about this one here? This is the methyl group at the end. In the In the coupled spectrum, we see a quartet because it's coupling to 3 protons. I mean, there's some extra lines here. That's TMS. That seems to be some sort of a, that little line there is maybe some sort of a impurity. But you can see we have 1, 2, 3, 4 lines, which is exactly what you'd expect in the coupled spectrum, because this carbon atom is then coupling directly to those 3 hydrogen atoms. 3 plus 1 is 4, we get a quartet. We switch off the coupling, we get a singlet, and so on. Another reason to do decoupling, particularly with insensitive nuclei like carbon-13, is because of this coupling, you end up losing, if you like, resolution a bit, right? And signals that are difficult to detect, you end up, you run the risk of not seeing. For example, in the coupled spectrum, or the undecoupled spectrum, it means the same thing, undecoupled or coupled, you don't see this carbonyl group, but in the decoupled spectrum you do. So generally, in fact, I've in my whole career never seen a coupled carbon-13 spectrum. It's always decoupled, right? It's always decoupled, and that's why when you report 13C NMR data, you should write it like that because it's decoupled from the 1H. Now, what we're going to talk a little bit about now are some different types, specific types of NMR experiments. And we have all these different pulse sequences and all these different techniques that one can employ for different reasons, for different situations. And one of them is inept. Right? Now what inept is very simply, this over here is a pulse sequence. So one writes, as I said, you can imagine we have these radio frequency pulses, right, at certain angles. Remember that first picture I showed you with the processing vectors? This is essentially a pulse sequence. And so is this at the bottom here. Inept is essentially a way of transferring exactly what it says, doing a so-called polarization transfer, taking an abundant nucleus like a proton and enhancing the signal of an insensitive nucleus, right? Now in order to do that, basically you need to know it has to be coupled to that nucleus. Typically, we use inept in 29 silicon NMR spectroscopy. So the silicon-29 is an example of a very low abundant nucleus, right? It's spin active, but it's an important nucleus, and you can do silicon-29 NMR spectroscopy. If you do so-called inverse gated, inverse gated 29 silicon NMR spectroscopy, it takes exceptionally long, right? You need a very concentrated sample, and routinely you have to record it the whole night just to get the signal. That's the sort of the standard routine one would employ to do a silicon for silicon-29 NMR spectroscopy. But with inept, what you can do is if you have protons attached to the silicon center or near to the silicon center, so J1 or J2, and you have an idea of what that coupling constant is, you can perform an inept spectrum, and within seconds, because of polarization transfer, actually detect the signal. That's great, because if you're a scientist and you, for example, want to, and you're working with silicon containing compounds and you want to see if a reaction is proceeding, you don't want to wait, the whole night to record a spectrum, so you make use of inepts. The disadvantage is you need to know what the coupling constant is. So what we're basically doing is if we take a compound like, let's say for example, something like this, what we're basically doing in inverse gated is we're just sort of doing a, let's say, standard spectrum, if you will. Of course, inverse gated means something different, but It's sort of the standard routine way of doing a silicon-29 spectrum. If I now do an inept spectrum, what I'm basically doing is I'm saying, all right, what is the 1JH silicon coupling constant? I input that into the program, and what it basically does is, by using this polarization transfer, boosts the signal of this nucleus, which is very low in natural abundance, inept. And you can apply inept to a range of other nuclei as well, but particularly we use it with silicon. Now, depth you have all encountered. I don't really want us to discuss this pulse sequence. I want us to go straight to the depth experiment. Now, what is depth?
So you can see which carbons have how many hydrogens?
Yes. That's one of the things. But you have different depth experiments. So depth stands for distortionless enhancement by polarization transfer, okay? We have different depth experiments, and here's basically the full range. At the bottom we have a normal 13C spectrum, right? Of course, actually, what is wrong with the way that I've written it? The bottom there. The bottom spectrum, I've made a mistake.
You said normal, but it's like decoupled?
Yes, it's decoupled. Probably, well, 99% decoupled, because you don't see any. Okay, that could be some sort of multiplicity pattern, but yeah. You can see you have nice sharp singlet lines, so it should be written 13C. It should be written like I've written it there, right? So don't forget this, guys. This is important. Yeah. So let's have a look at these different depth experiments. All right. You have different depth experiments at different theta angles, which is sort of the pulse. So at a depth 45 spectrum, will show what? Well, basically all protonated carbons, right? You will see all protonated carbons. So any carbon atom that contains a proton, a J1 coupling to a proton. You won't see quaternary carbons, and you won't see the deuterated solvent. Now that's very useful. Why is it useful not to see the deuterated solvent?
Then you can assign for sure the
Well, it could be that you have signals which are sort of hidden under the solvent, right? That very often happens. And if you want to see if there's a signal corresponding to your compound, you can simply record a depth spectrum, a depth 45 spectrum, and that's a way of making sure that there's nothing hiding there. But remember, you're only going to see see it if it's there, if it's protonated. If it's a quaternary carbon, you're not going to see it. Yes.
And also, like, if we have a lot of solvent, and like, for example, if our sample is not saturated enough, it will probably also have like a huge peak of abundance, and like downplay the rest of them.
Yes, yes, that's why it's important to make sure that you have the right concentration of the sample. Now, this brings me to another point before I proceed, a very important point. When we look at an NMR spectrum, right, let's start off with a proton NMR spectrum. So I'm going to digress for a moment, forgive me for that. But, this is important stuff. All of you have recorded proton NMR spectra. And let's take, by the way, solvents, if you're an organometallic chemist working with sensitive compounds, the typical solvents of choice is C6D6, deuterated benzene. We don't use deuterated chloroform or deuterated methylene chloride because they're quite reactive. We certainly don't use DMSO because that just kills everything. But we use deuterated benzene because it's a nice, stable, inert, aromatic solvent. Now, if you record an NMR spectrum of deuterated benzene, just of deuterated benzene, you see a signal at 7.15 ppm. Now, what is that? There's a signal.
So it's the mandate of solvent.
Correct. People make a mistake of saying, oh, this is the deuterated solvent. You must be very careful. It's not the deuterated solvent. What that signal actually corresponds to, remember, we don't have 100% deuteration. We have like 99.95% or 0.5% deuteration. This is in fact, this corresponds to C6D5H. Right? Tiny amounts of it present because it's not fully deuterated. Same thing in the carbon-13 spectrum. For benzene, it's at 128, and we see 3 lines. We see 3 lines. That correspond, what are those 3 lines? In a 1:1:1 ratio. It is basically what the 3 lines are is the 13C nucleus coupling to deuterium. Deuterium has a spin of 1, so we end up with what looks like a triplet, but it's not a traditional triplet. It's actually a 1:1:1 signal. A traditional triplet is 1:2:1. This is 1:1:1. And I think you might have seen similar things with the solvents that you've been using in the practical. So be aware of that. In the proton NMR spectrum, it's basically corresponding to something like that. In the 13C, it is the multiplicity is as a result of coupling to deuterium. Right. So that's an important technical point. Let's get back now to the depth spectrum. We can also record a depth 90 spectrum. And if we record a depth 90 spectrum, this is very useful because that only shows us singly protonated carbon atoms. You see, this is very important when we're trying to assign something, to record all these different depth spectra. It's very useful. And the most commonly used depth spectrum is the 135, depth 135. And that shows, and that gives us a very nice sort of summary, if you will. The CHs are up, the CH2s are down, and the CH3s are up. So for example, you can clearly see, just by recording the spectrum, that these 2 pointing down correspond to a methylene group. So in your future chemical work, recording depth spectra can be quite useful. If you do 2-dimensional correlation spectroscopy, it's not necessary to do that because you do the assignment in a more rigorous way. This is sort of a middle of the road. If you're too lazy to do the 2-dimensional correlation spectroscopy, you can sort of play around with these things here. Now let's talk about 2D NMR. Now we've spoken about 1-dimensional NMR. We've looked at some different nuclei. We have, we're going to come back to this a little bit later on. I just sort of now in the first part of the lecture want to sort of get through the mechanics of it, and then we're going to, in the second part, look at some actual examples. Now, what is a 2-dimensional NMR spectrum? Well, a 1-dimensional NMR spectrum is a spectrum that has one frequency domain. It has one frequency domain, which we get from a free induction decay signal, which has undergone a Fourier transform. A 2-dimensional NMR spectrum is simply a spectrum that has 2 frequency domains. Very simple. Now, this business of 2-dimensional NMR spectroscopy actually started only in the early 70s. So you can see this is really actually early to late 70s. So this is something that's very modern, right? I mean, this is not something that's always been around. NMR spectroscopy, 1D, has been around, I guess, in use in chemistry since the 1950s. But of course, 2D NMR spectroscopy came much later from these guys here. And this guy won a Nobel Prize, Ernst, for his contributions to this. And he's from ETH Zurich, which is, I would say, the best, well, it's just a personal opinion, I think it's the best university for chemistry in Europe. They've got really excellent people working there. So if some of you are thinking about grad school, if you can get into ETH, I would drop everything and go immediately. This guy won a Nobel Prize for his contributions to 2D NMR spectroscopy, and several other Nobel Prizes have also been awarded for two-dimensional NMR spectroscopy, which is exceptionally powerful, particularly in the elucidation of large biomolecules, proteins. People have actually recorded NMR spectra of proteins, and using two-dimensional NMR spectroscopy with very high resolution, managed to actually assign every proton, right, using a range of different 2D NMR techniques, and even figuring out the structure of the protein, inferring the structure, the three-dimensional solution structure from the 2D spectrum. That's quite remarkable. It's possible to do that. If you have a highly resolved two-dimensional spectrum and you use all sorts of different 2D techniques, it is indeed possible to do that. Of course, we're all familiar with MRI scanners. I mean, this is sort of a spin-off of the technology that comes from nuclear magnetic resonance. You see, this is a beautiful example of how, you know, university academic research led to something that's very useful in medicine. It started off with physicists looking at nuclear magnetic resonance, then chemists picked it up, and then doctors picked it up, essentially. You see, that's a very important progression. That's how science works. So I don't know if any of you have been for one of these scans. I haven't been for one of them, but as you know, it gives beautiful, highly resolved images of tissue. And if you like, it essentially relies on finding where the water is. Water makes up most of the body, and so it's a map of water, essentially, MRI. So, we, like I just said, normal one-dimensional NMR spectroscopy, we've got frequency domain, one frequency domain. Two-dimensional NMR spectroscopy, we've got two frequency domains. And this is sort of a pictorial representation of the mathematics going on. Free induction decay, Fourier transform 1D spectrum. A series of free induction decays here, because we're working in two dimensions. Then a Fourier transform, and we get a two-dimensional spectrum. Now this is very useful. Well, this is very useful because, as I said, it really enables us to actually look at couplings to see where things are in a molecule. And you guys have been doing this in the practical course, you know, sort of hands-on, and I made a point of that. I can assure you that in no other university, in a 3000 practical course, be told in an inorganic practical course to do 2D NMR spectroscopy. And the reason why I did that is because it is very important, it is rigorous, it is a rigorous way of making sure that the assignments are correct. Many people don't do this these days. Many people guess assignments. Okay, well, sometimes it's obvious, but sometimes it's not obvious, you know? And you might think that an assignment in a 13C spectrum looks perfectly reasonable, but you know, you have to do the 2D NMR spectroscopy to be sure. So that's my message for you going forward. It doesn't cost anything to record an HH-COSY, an HSQC, and HMBC. Just always do them routinely for everything, so that you have the data. That's sort of the school that I come from, right? I mean, that's sort of a very rigorous way of doing it. Other people would say, oh, come on, it takes too much time, just record the 13C, and if you can't assign all the signals, it doesn't matter. I find that a very sloppy way of doing things. The better way to do it is to do the 2D NMR spectroscopy, and to sit on it, and to do the assignment. That is the scientific way. Right. Now, there's actually two ways that we can represent 2D spectra. Now we have a range of different types of two-dimensional NMR spectroscopy, which some of you already, well, you're all familiar with it from the practical course. But we can represent it in two different ways. We can represent it in 3 dimensions as a stacked plot, which kind of looks very cool. But the problem with that is that it's difficult to actually locate the exact peak position. So generally, we, as you know, use a contour plot, which is essentially just taking a slice of the stacked plot, right, and looking at it. The advantage of that is you can pinpoint the exact location of the so-called cross peak. So this is what a cross peak looks like in a two-dimensional spectrum. There's advantages and there's disadvantages, but I can assure you that I personally have never worked with these. One always generally works with us. This is kind of just cool to look at, and it's useful because sometimes you have extremely weak cross peaks that you cannot see in let's say a slice of this thing here. And if you do it in 3 dimensions, you can actually see that there's a real signal there, right? And very often that's important. Because if you increase the resolution here, you guys have again experienced this. You don't know if it's a real peak or if it's just noise. So to pick out a signal from noise, this is better. To get the actual peak position or the cross peak position, the contour plot is better. Okay. Now, we talk about a diagonal. Now, if we're doing homonuclear correlation, of which HH cozy is the most important, I see that, yeah, of which HH cozy is the most important, the off-diagonal cross peaks are the most important, right? So here we have an example at the bottom. This is, let's say, an HH correlation spectrum of some compound. And here we have two resonance signals, 2 sets of signals. And basically how this works is, as you guys have some practical experience with, this is just to pin it down. You go down to the main diagonal, and you always see along the main diagonal a cluster of peaks. Those are not important. But you go down to the main diagonal in a homodinuclear, for example, HH cozy spectrum, you go across, you go up. That means that this signal and this signal are related. It means that this proton, let's say, and this proton are coupling to each other. Potentially, let's say we are J3 coupling. We can play the game the other way around. We can look at this signal here. We go down, we see a cross peak. We go across to the main diagonal, we see a cross peak, obviously. Well, that doesn't have, well, there will always be a cross peak there. There's a lot of stuff on the main diagonal. And then up again. So you can do it either that way or that way. Another way of doing it is we can go like this. We can say, okay, we can look at the y-axis, or the frequent, or let's call it the F2 axis, the F1 and the F2 axis, so the 2 different frequency domains, and you can do it in that way as well. You see, it's a highly symmetrical pattern about this diagonal. So does everyone sort of get that? And that's how we deal with the homodinuclear correlation spectrum. Okay, next. Don't worry about this. We call this in general cozy, correlation spectroscopy. We have different types of cozies. This is what we've just looked at, an HH cozy, right? So this is a homodinuclear spectrum with 2 frequency domains which are identical in terms of the nucleus. And here you can, for example, see a typical pattern of 2 protons that are correlated to each other. In other words, 2 that are coupling to each other. And this is due to a so-called polarization transfer, right? And you can see that this is sort of the situation. So again, if H2 is coupling to H1, down to the main diagonal, across and up again, it's a little bit, that should be a little bit more to the left and a little bit more to the right, but okay, you get the picture. Or alternatively, you can play the game like this. Da, 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 right? And of course, we'd on this side also have H1 and H2. So you have two spectra that are identical, two identical frequency domains, and you have a main diagonal, and you look at the off-diagonal signals. And the off-diagonal signals will tell you if there's coupling. Now a note on that, right? What sort of couplings do you see? Well, if it's homodinuclear, you would see, for example, H1 couplings, you'd see H2 couplings, you'd see H3 coupling, sorry, not H, J3 couplings, J1, J2, J3. With J4, so for example, if we imagine something like this, for argument's sake, this one of these protons and this proton here, that's a J4. That would be a J4 coupling. Now that one typically does not see. That one typically does not see, but sometimes you do. But it's very, very, very weak. It will be a very weak cross peak, but typically you see J3. Right. So you would see in a spectrum, we'll look at an example in a minute, you could see a J4, it would be very weak. If you're lucky, generally you don't. But you would, for example, see a very strong cross peak between these protons here and these protons here, because that's J3, right? And that really helps you in the assignments very often. So here we have an example. This is a homonuclear correlation spectrum, an HH, happens to be an HH cozy for ethanol. Now what do you see? Let's look at that. This is the spectrum, this is the correlation spectrum. How many signals do we expect for ethanol? Let's start with basics. How many sets of signals?
3.
3. Corresponding to what?
CH3, CH2, OH.
Correct. CH3, CH2, and OH. So let's look at that. Is that what we see? Do we see 3 sets of signals? Yeah. We see a triplet, some weird little broad signal, and what is that? Right, so which is which here? I mean, we already know, right? Because it's a simple molecule. We don't need to do the 2D spectrums. It's kind of stupid. But we do it anyway, just by way of example. What does the triplet correspond to? CH? CH? 3. Yes. What does the quartet correspond to?
CH2.
No one?
OH.
Right. OH is as far away, it's not coupling to anything, and OHs tend to be quite difficult to see. All right. So let's have a look at this. Let's have a look at this. Here you can see I've drawn all the correlations, but I mean, let's just focus our attention on this spectrum here. If we look at the triplet, which we've correctly said corresponds to the CH3, check it out. We go down to the main diagonal. You see we've got lots of stuff happening always on the main diagonal. There's always going to be cross peaks actually for every signal there. Go down, we look left, we look right. We look left, we see there's a cross peak, and we go up again. What is the conclusion? The conclusion is that the triplet and the quartet are coupling to each other. What is the conclusion? The conclusion is that they are probably related to each other by a J3 coupling, right? And that's exactly what we have in the molecule, because that is the CH3 and that's the CH2. And you see we have a very strong cross peak there, right? Now, let's look at what else do we see? What other cross peaks do we see? Let's look at the signal. Does it have any cross peaks? We go down, we'll go across. Oh, there's a cross peak, we go up. So this is coupling to the cortex. Is that what we expect? Yes, because this is the alcohol group. Now let's pretend we didn't know the structure. You see, now we can deduce the structure from the 2D spectrum. It's a stupid, simple molecule, but using the HH cozy, we can actually rigorously figure out what is what, right? That's why I'm showing this example. So indeed, this OH is corresponding to this quartet. So, and that's exactly what we expect, because it would be a J3 coupling. 1, 2, 3. Now let's look at everything from the perspective of this baby here, the quartet. Now check it out. What do? We always go down to the main diagonal. There it is. There's a big cross peak. We look left, we look right. What do we see? We don't see anything to the right, but, sorry, to the left, but we do see something to the right. What do we see? We see two cross peaks, right? And that's exactly what we expect. In other words, what is the conclusion? That CH2 is coupling to both CH3 and OH. That's how it works. Now, talking about homonuclear correlation, in this typical correlation, two-dimensional correlation experiment, we just looking at J3 couplings essentially and J2 and so on. But it's also possible that there's all sorts of other experiments that have been done which looks at total correlations. In other words, we have an example called TOXI, which is total correlation spectroscopy, which looks at the correlation of all protons within a spin system, right? So you will obviously in a TOXI spectrum see a lot more cross peaks than in a normal, let's say, homonuclear spectrum where you just essentially see, let's say, up to J3. So that's what TOXI is. At the bottom here is that these are all these funny diagrams here. These are the so-called pulse sequences. So what people do is they sit and write pulse sequences to do these NMR experiments, right? And that requires a lot of skill. But yeah, it's possible to do that. You can sit down and write pulse sequences. And I had a colleague in Berlin that used to write all sorts of crazy pulse sequences to do all sorts of weird experiments, right? So you can invent new pulse sequences and new NMR experiments. Say, for example, if you want to look at the correlation between a proton and a phosphorus atom, but only see the J3 correlation and not anything else, you can write a pulse sequence to do that in principle. You can do anything. All right, so that's TOXI. Now, very important, another sort of variation on the theme in terms of homonuclear correlation is so-called nosy. Who's heard of nosy? Right, so what's nosy? Tell us. Mitch? I don't want to do that. All right. But you guys have heard about it. But
yeah, we did saw it.
all right. So what nosy is, right, that's the pulse sequence corresponding to a nosy spectrum. It's nuclear Overhauser effect spectroscopy. What is the nuclear Overhauser effect?
It's like coupling within proteins between genes.
Yes, kind of. It is of relevance in proteins. It's coupling through space, right? So instead of coupling through an actual sigma-bonded framework, like is generally the case, nuclear Overhauser effect is coupling through space. And that's what nosy is all about. Nosy is about looking at coupling through space, which of course is of paramount importance if you want to do structural elucidation of a protein, for example, because you want to know which protons are close to which protons in space. So we use a nosy spectrum. This is an example of a nosy spectrum for aspirin, acetylsalicylic acid. What do you see? Let's focus your attention on C9. Oh, sorry, on the proton in the CH3 group, right at the end. That's CH3.
As close to one of the frozen hydrogens.
Sorry?
Overspace is close to one of the benzene hydrogen.
Correct. This CH3 in space, because remember there's lots of flexibility about this OC group, it's spinning around like a rotor, and it's going to, at some stage during that process, be close spatially to the C2H over here. And we're going to see a cross peak in the noisy spectrum, and then you see it. There's a tiny cross peak. That signal corresponds to the C2H, right? So you can, for example, imagine assigning this doing a what? What would you do to assign all the H's? Yeah, it's just a normal HH cozy, so you assign everything, so you know what is what. Then you record a nosy spectrum, and that's sort of additional confirmation. You see, okay, there's a cross peak there, so that fits with with the expectations. That's basically how a nosy spectrum works. Now, this is a very simple compound, but if you record a nosy spectrum of a protein, right, you can actually, you'll see lots and lots of cross peaks, and it enables you to actually elucidate the three-dimensional structure of a protein. And here are some notes on that. Actually, you can, as I said, depending on the strength of the coupling, you can even estimate the distances, really, within a very high degree of accuracy. That's quite wild, right? You just record a spectrum, you can actually elucidate the 3D morphology of a complex biomolecule employing this, and within a 10% accuracy. Just one final note on nosy. The nuclear Overhauser effect is rather weak for large molecules. So we have another NMR experiment, which I just want to briefly mention, called ROSY, which is rotating frame nuclear Overhauser effect spectroscopy, which is a way of actually enhancing the nuclear Overhauser effect for large immobile molecules. And because remember, if something is immobile, the nuclear Overhauser effect, in other words, coupling through space, is going to be sort of switched off, or it's going to be a much weaker. So this is an alternative. ROSY is, if you like, a type of nosy. Okay. Now, I want to, so we've now looked at homodinuclear experiments, particularly nosy, ROSY, and HH, and all these stuff. What I now want to talk about is heteronuclear correlation, which is even more powerful, because now we're looking at correlation between an H and an X nucleus. So HX correlation, where X is a heteronucleus. All right. Now, again, you've encountered this in your practical. By the way, I think next year I'm going to do this lecture first, and so that you have it for some background for the practical. Didn't think about that. This is the pulse sequence for a heteronuclear correlation spectrum, in this case an HC COSY. Now, traditionally when this started, they called it HETCORE. That was the sort of the abbreviation for it. That's the old-fashioned abbreviation for this from the 80s, right? And this is the original pulse sequence for a HETCORE. In this case 13CH, you have a 90-degree pulse. You have a 90-degree pulse in the 1H channel. You have a delay, and then you apply another 90-degree pulse. At the same time, in the 13C channel, you apply a 90-degree pulse, and then you allow the free induction decay to take place, and you do a Fourier transform over both channels, and you end up with a 2D spectrum. In fact, it's simpler to interpret a heteronuclear correlation spectrum, because what's sometimes confusing in a homonuclear correlation spectrum is you have this diagonal, you've got to go down to the diagonal, across and up again. Here you just see cross peaks. So you're going to have two frequency domains corresponding to two different nuclei, for example, typically proton and carbon-13. And on let's say the x-axis, you'll generally, let's say, have the carbon, and sorry, the x-axis, yeah, on the y-axis you'll have the carbon, on the x-axis the proton. And as you all know, you will have the proton NMR spectrum there, the 13C spectrum there, and you will see cross peaks. These cross peaks, it now depends on what sort of 2D heteronuclear NMR experiment you're doing. Okay? And here we have the het core, the old-fashioned two-dimensional NMR spectrum, which shows only J1 couplings. In other words, you're going to see cross peaks between protons and carbons to which they're directly attached. So here we have an example, cis-hex-3-enol. Some of you have done this in the spectroscopy course, I know, but it's good for some revision. But you can clearly see the cross peaks. So I think on that note we're going to stop and we're going to have a break of 10 minutes. When we come back, we're going to look at the spectrum, and we're going to pick up the pace of it, right? Because in the second part of the lecture, we're going to get our teeth stuck into organometallic chemistry.